Okay, well, this is the second half of the respiratory physiology notes that will be taking the place of the class on Wednesday, February 18th. So this material won't be covered in class. It'll just be covered on this presentation. So make sure you listen to this and fill out the notes as you do. Okay, so this is where we left off with class today on Monday, and we talked about these different pressures changing, and what happens in this last point that we left off with here is with the diaphragm relaxing, it pushes up, right? And then we see what happens to this cavity here, this intrapleural space gets smaller. So that means the volume goes down, right? So volume goes down. According to Boyle's law, pressure is going to do the opposite, which would be go up. Okay, so pressure goes up, then it's going to push on the lungs. Okay, and then that extra pressure on the lungs is going to make the lungs smaller. All right, so we'll see this here, diaphragm relaxing. Okay, and what does that do? That we notice the pressure is greater in here now, from 750 to 754. That takes away some of that vacuum that's there in the lungs. Doesn't suck out as much in the lungs, actually pushes in just a little bit. And that allows the lungs to recoil because they're elastic, and the volume of the lungs is now going to go down. If volume goes down, according to Boyle's law, pressure goes up, right? So now you'll notice pressure in the lungs is greater than pressure in the atmosphere. So if the mouth is open, just due to diffusion, air is going to exit. Okay, that's what we see, increased intrapleural pressure. So pushing in on the lungs, and we get air moving out of the lungs. Okay, that's pretty much that. So let's, and then if we go back to resting period, we have an equalization of pressure on the outside of the body and pressure in the lungs, and no air movement. So we're back to where we started. So make sure you know this chain of events and know not just the changes in the lungs, but also the changes in the intrapleural space. Okay, so this next small section we'll be looking at the how a spirometer works and how the different and pretty much defining the different lung volumes that a spirometer measures. And so this is what an old school spirometer would do. A person would breathe into this, which would add some air to this drum or to this cylinder here, and make that drum or the cylinder less or more buoyant, less dense, and so that would lift it up. And then you notice the cylinder is connected to a wire here, some kind of a string, and that is attached to a pen over here. And so as this lifts up, this pen moves down. And so it goes up and down with that, and that creates a line on this. And there's a little piece of paper that this pen is using. And so now most of these are electronic, but this was kind of the original idea. This next slide shows the different volumes here, okay? And so a few things to note here that are important. One, this movement up and down, so going up is breathing in, going down is breathing out. Okay, so this is somebody breathing into a device. It goes up and then they exhale and it goes out. Okay, these small increases and decreases, this is known as tidal volume. Okay, so this is just normal breathing in and out. Typical tidal volume is about half a liter, about 500 milliliters. Okay, that's important to know. All right, then what you usually do on these tests is you have the person take as deep of a breath in as they possibly can. Okay, so they do a couple normal breaths here, and then deep in as they possibly can. Okay, this is going to lead to maximal inspiration. Okay, so what they did is they tapped in to their inspiratory capacity that they were kind of holding it on, reserving, kind of. Okay, so we call that the difference between tidal volume and total ability to inspire is called inspiratory reserve volume. Okay, so if you add these two up, tidal volume and inspiratory reserve volume, you get inspiratory capacity. Okay, now what you do with this test, after they take that deep breath in, you let them breathe it out normally, take another normal breath, and then the next one you blow out as hard as you possibly can, blow all the air out of the lungs until no more can come out, and that gets you down to maximum expiration. Okay, so just like on the other side, now we have an expiratory reserve volume. That's tidal volume plus the amount of air that was blown out. With expiratory reserve volume, it's just that extra amount of air that was blown out above tidal volume, and that's that. So then if we add together inspiratory reserve volume, tidal volume, and expiratory reserve volume, we get what's called vital capacity. And really, vital capacity is the total movable amount of air in your lungs. Okay, that's that. So then, if we want to look at one other volume, this volume down here is residual volume. This is the volume that we can't move in our lungs. This is the amount of air that's just stuck in our lungs, even if we breathe out fully. This is a good thing. If we were able to breathe all the air out of our lungs, we would lose all pressure in there, and the lungs would collapse. So we always need to have some level of residual volume. So as far as these capacities go, if we add up inspiratory reserve volume plus tidal volume plus expiratory reserve volume plus residual volume, we get total lung capacity. Okay? If we take that total movable amount of air, which is vital capacity, and add residual volume, then we also get total lung capacity. So the capacities here are all calculated by adding up volumes. Okay, so the first one, inspiratory capacity, is inspiratory reserve volume plus tidal volume. Okay, functional residual capacity is expiratory reserve volume plus residual volume. Okay, and then we have vital capacity, which is inspiratory reserve volume plus tidal volume plus expiratory reserve volume, and that is really the total movable amount of air. And then if we take total lung capacity, we get this vital capacity, which is here, plus residual volume. And that's it. So you just need to know how those things are calculated. Okay, so obviously the main job of the respiratory system is to get oxygen out of the atmosphere and into the blood, and to get CO2 out of the blood and back into the atmosphere. Okay, and this is just kind of looking at the overall picture of that. Okay, so in order to kind of get a full grasp on what's going on with the respiratory system, we need to know how to calculate partial pressures of gases. Okay, and so in order to calculate partial pressures of gases, we need to know the total pressure of the atmosphere first, and then really all partial pressure means is what percentage of that total pressure is created by each gas. Okay, so if we think about this in terms of being underwater, we know that if we go underwater, the deeper we go, the more pressure we have on our body, right? We feel that in our ears. We have to clear our ears, and so we need to be able to deal with that pressure when we go deeper underwater by clearing our ears, and that's because we have more water on top of us. So that all that water, the weight of that water is on top of us, and that's the pressure we feel. So it's actually the same thing with air. When we are right at sea level, we have a lot of air on top of us. All the air between the top of the atmosphere and us is weighing down on top of us. It all has a weight. If we go up to the top of a mountain that's 15,000 feet tall, we have a lot less air on top of us, so that atmospheric pressure is less. Okay, so in order to calculate partial pressure, we need to know the percentage of each gas, and then we also need to know the total atmospheric pressure. So at sea level, total atmospheric pressure is about 760 millimeters of mercury. Okay, but in order to calculate partial pressure of each of these gases, we need to know the percentage of each. Okay, so here they are. Nitrogen is typically is always going to be the highest, and that's about 79.04% nitrogen. Oxygen's about 20.93%, and carbon dioxide somewhere around 0.03%. And these vary a little bit, but those are just numbers we can use here. Okay, so then if we want to calculate partial pressure of each of these gases at an atmospheric pressure of 760, we take 0.7904, which would be the same as 79%, times it by 760. What does that give us? It gives us 600.7 millimeters of mercury. If we want to do it for oxygen, we take 0.2093 times 760, gives us 159.1. Want to do it for CO2, we take 0.0003 times 760, and you get 0.2. So you're just moving this over 2 decimal places and then timesing that by the total atmospheric pressure. And so if you add all these up, you're going to get 760. Okay, and that's how that works. So the only thing that's going to change partial pressure of a gas is a change in total atmospheric pressure, because these percentages don't change. Okay, percentages stay the same, but atmospheric pressure differs. Okay, so you'll definitely need to know how to calculate that at all different atmospheric pressures. Okay, so I'm going to let you guys do these clicker questions on your own. We're not going to go through these, and if you have questions on them, you can let me know. The steps in the oxygen cascade are pretty clear, and don't worry about the 5 here, but just it's mainly understanding each of these steps along the way, definitely knowing what this partial pressure typically is in the mitochondria, and knowing what this partial pressure typically is in the air, depending on the atmosphere. And then a couple other key things are one of the big reasons there's so much surface area in the mitochondria is because that allows for a lower partial pressure, because it spreads out the little bit of oxygen that's in there so much through all those different layers of the mitochondria, and that gives it 500 times greater surface area than that of hemoglobin. Okay, the other thing is myoglobin has a very high affinity for oxygen, so it's pulling on oxygen very hard to grab a hold of it, pull it out of the interstitial space. Okay, and so the key here is that even if we breathe in air, if say we're at the top of a mountain, even if we breathe in air that has a much lower partial pressure, then we're still going to be able to get it all the way down to the mitochondria. But what has to happen is each of these steps has to drop. Okay, so when you're at the top of something like Mount Whitney, your partial pressure of oxygen might be only 90 degrees or 90 millimeters of mercury in the air. So that means this is going to have to drop quite a bit, probably closer to 70. This is going to have to drop even more, probably closer to 50. This is going to have to be way lower, probably closer to 20. And so each step, this diffusion gradient is going to be less, and so it's going to be harder to pull oxygen from one step to the next, but we're still going to get it down to the mitochondria, it just might not get as much. So that's a key thing in understanding, which we'll talk more about when we get to the altitude section. And this is really showing that same idea here, that it happens with oxygen. Okay, we have this step with oxygen going down. Here's that partial pressure in the capillary, partial pressure in the cells that we talked about of 20. Okay, and we see the same thing with CO2. We have a highest concentration of CO2 at the cells and the lowest in the lungs. That way we can always send the CO2 out of the blood back into the lungs. Okay, and this is really showing the same idea. We don't really need to talk about this too much more, but this is just showing that we have a decrease in partial pressure for oxygen from the lungs to the blood, whereas CO2 it's the opposite. We have a decrease in partial pressure of CO2 from the blood to the lungs, because that's the direction we want those gases to move. Okay, and as I mentioned, myoglobin has a very high affinity for oxygen, meaning that it grabs on oxygen and pulls on it very hard. And so this, when there's myoglobin present in cells, in muscle cells, it's going to have a much stronger pull on oxygen, be able to pull oxygen out of the blood much easier. And so myoglobin is a specialized protein that's only found in muscle that allows it to get oxygen out. So we'll talk a little bit about each of the about oxygen and CO2 and how they're carried in the blood. Okay, as you guys probably know, hemoglobin carries the majority of oxygen. Okay, it's 98%. So almost all the oxygen in the blood or in the body is carried in hemoglobin. So there's a small amount that just dissolves into plasma, only about 2% or less. And one interesting thing to note, as it shows here, is each hemoglobin carries 4 oxygen molecules. Okay, so 4 O2s. So you can see each hemoglobin has 4 O2s bound to it. Okay, with the carbon dioxide, we have about 60 to 70% of it carried in the form of bicarbonate. Okay, so this is the bicarbonate ion, very important for the buffering system. And so the equation that we've talked about a little bit in class already, but we'll talk about more in the acid-base balance section, is right here. So bicarbonate ion is right here. Bicarbonate readily binds with hydrogen ions, turns into carbonic acid, which is this one in the middle, and then that dissociates into CO2 and water. And so bicarbonate will pick up hydrogen ions out of the muscle cell where they're created. That blood is then sent to the lungs, where it can carbonic acid can dissociate into CO2 and water, and the CO2 is breathed out of the lungs. Okay, and so we also have a little bit of CO2 carried in the plasma, about 7 to 10% of CO2 that's just dissolved into the plasma. And then we have a little bit carried in hemoglobin as well. It's not its main job to carry CO2, but some of it is carried in hemoglobin. It's about somewhere around 20% is carried in hemoglobin. Okay, and so that is how CO2 is transported in the body. Okay, one important concept to understand with the this oxygen carrying capacity of blood is this idea of the oxygen hemoglobin dissociation curve. And so two main things you need to look at here. One is this x-axis, which is looking at the partial pressure of oxygen in the blood. Okay, and then this is the percentage of oxygen or percentage of hemoglobin that's saturated with oxygen. Okay, and so we talked about the blood at the arteries right past the lungs after the oxygen has been put onto the blood. That's at a partial pressure of about 95. Okay, so that's about right here on the x-axis. So if we go up and see where that intersects with this line, we see that about 98% of the hemoglobin is saturated with oxygen. Okay, and this is pretty much where we live at. If we have a fully functioning respiratory system, we live at about 98% saturated, which is totally normal. Okay, and that's what this shows. Okay, so what we're going to look at really is how certain things shift this curve and why that's important. Okay, so all of these next three slides, I'll show three things that shift the curve. Okay, and the thing to think about with this is every time we see a rightward shift of this curve, that means that we have all three of the things are going to be byproducts of more metabolism. Okay, so rightward shift means something related to more metabolism happening, more use of ATP, more use of oxygen. Okay, a leftward shift is going to be just the opposite. A leftward shift is going to be the result of less metabolism happening, less use of oxygen. Okay, so the first one's a hydrogen ion. Okay, so we see this rightward shift here, going from the black line to the blue line. And so with high hydrogen ion concentration or low pH, we have a rightward shift. Okay, so let's see what that does at a partial pressure of 40, which is typically the partial pressure when we're down close to the muscle cell. Okay, so partial pressure of 40, when we just have a normal curve without the shift, we're right at about 78 or so % saturated. Okay, but if we have a rightward shift, because we have high hydrogen ion concentration, meaning that we've been doing a lot of metabolism, let's see where we are saturated now. Actually down to 60%. So the question you have to ask yourself is, why would we want to be less saturated in an area that has high metabolism? Okay, and the answer is because that means we're able to drop off more oxygen. Okay, so higher metabolism means we're dropping off more oxygen. Okay, and that's what we want. We want to drop off more oxygen when we have a lot of metabolism going on. That means we're using a lot of oxygen. Okay, and that's exactly what that shows. If we're not using a lot of oxygen and not doing a lot of metabolism, then we have a leftward shift of the curve, and that means we go from being 78% saturated to about 82% saturated, meaning that we didn't drop off as much oxygen. That's good too, because we don't need it if we're not doing that much metabolism, right? So that's the way you want to think about that. Do the same thing for CO2. You can do the same thing with the lines here, okay, with the rightward shift, the leftward shift. High CO2 is a byproduct of the Krebs cycle, right? So if we're doing a lot of metabolism, we're making a lot of CO2. That means we're going to want to be less saturated at any given point. So using this example of 30, we go from here at about 50% saturated down to about 30% saturated. That's what we want. We want to drop off more oxygen if we're making more CO2, because that means we're using more oxygen. And it's the same thing with temperature. The higher the temperature goes, the further this shifts to the right. The lower it goes, the further it shifts to the left. Meaning higher temperature due to increased breakdown of ATP and formation of ATP, that loss of heat, right? That's going to mean we want to drop off more oxygen because we've used more oxygen. Okay, and so one thing that's nice to bring up at this point is this idea that when we're hiking at altitude, when we're at altitude, we can calculate the partial pressure of a gas. Okay, and so at the top of Mount Everest, total atmospheric pressure is 250 millimeters of mercury. Okay, so when we want to get the partial pressure of that gas, which is oxygen, we take 0.21 times it by 250, and that's going to give us 52 millimeters of mercury. Okay, so that means that the pressure of oxygen in the air is already down to almost what it is in the interstitial space normally. Okay, so we went from 150 millimeters of mercury in the air to 52. So that means every step along the way is going to have to drop significantly in order to still have a movement, a jump down, and still have a concentration gradient. So it's very hard to get oxygen down to the mitochondria at this altitude, but you can still do it because that mitochondria partial pressure is so low, but it's very hard to do so. We'll get into that a lot more in the altitude section. We'll just leave it at this for now. Okay, and so we need to talk a little bit about things that control breathing, control respiration. And so we've already talked about this a little bit in terms of the ventilatory threshold and how it's related to lactate threshold. And we talked about one key chemical that stimulates those chemoreceptors and causes you to breathe more. Okay, and we talked about how CO2 is the main driver of ventilation. So the more CO2 you have, the more you breathe. Okay, that's the main thing. But they're also sensing levels of oxygen, so decreased oxygen will drive breathing, as well as decreased pH or increased hydrogen ions. Those will also drive breathing. Okay, also we find those peripherally as well as centrally. Okay, and another interesting thing is the start of expiration occurs via this reflex called the Hering-Brewer reflex. And so there's stretch receptors in the lungs that are constantly sensing how far stretched the lungs are. And when they reach a certain point, those stretch receptors are stimulated. And what that does, that starts a reflex loop, which pretty much causes the diaphragm to relax. It inhibits the diaphragm, so the diaphragm relaxes and pushes up the lungs, and we expire the air. Okay. Not lately, but in the past 10 to 20 years, we've also been seeing some research coming out that proprioceptors in muscles and joints are also intricately involved in controlling respiration. We don't understand how this all works, but we know that somehow these mechanoreceptors found out there are involved in this, as well as pain receptors, as well as emotional stimuli. So all these things are related, but the key things I want you to understand are the chemoreceptors and this what starts expiration. All right, guys, that'll do it for this. We'll see you guys on Friday. Make sure that you are ready to start the cardiorespiratory acute response to exercise, and that you're ready with the quiz on Friday. We'll see you then. Bye-bye.